So in the next few chapters, chapters 3, 4, and 5, we're going to change gears a little bit and we're going to talk about probability. So I'm sure this is a term that you are familiar with. You probably know probability as the chance of an event occurring. And that's exactly what we're going to be looking at here. Now, it's important to note there are three different types of probabilities. There is a subjective probability, which is that would be like the percentages that you hear in a weather report. You know, there's a 30% chance of rain. They're based a little bit more on an estimate. They may be based a little bit more on opinion, but they're not based on a definite formula or data that's been collected or anything like that. So we're going to try to kind of stay away from those, from the subjective ones, and we're going to focus more on classical and empirical probabilities. So we're going to start with a classical case, and classical just means that everything that could happen in the experiment has the same chance of occurring. So this is going to be like, you know, you roll a die, you flip a coin, you select a card, any type of thing where all the different outcomes have an equal chance of occurring. So you'll notice here the first thing you see is just a basic definition or formula, if you want to look at it that way, for how we're going to be calculating probability for any possible event. All right, now first thing is to understand notation, because you are going to see this shorthand used a good bit. So when you see this P of E, as you might guess, the capital P there says we are calculating the probability of an event, and whatever event you want to look at is going to be in parentheses. All right, so just to show you what this is going to look like, the first example that we have down here says if you roll a 6-sided die, find the probability of rolling a 2. So the way that I could write this would be P of 2. All right, again, probability and then event we want is a 2, and that's what we put in parentheses. Now what our formula says is first, now everything's going to be done in terms of number of outcomes. So it says first, let's look at just the number of outcomes in your particular event. All right, so if we think about what could possibly happen in this experiment, if we wanted to even write down the possible outcomes, this is called the sample space of the experiment. If we're going to roll a 6-sided die, then we could list out our possible outcomes 1 through 6. Right, so looking at the sample space, you should be able to see that this event of rolling a 2, it only looks at one possible outcome in the sample space. You could also look at it as there's only one way that you can roll a 2. So I'm going to take that 1, and to get probability, I'm always going to divide by the total number of outcomes. And for a 6-sided die, you can look at your sample space, all right, count them up. You've got 6 total outcomes, 6 different things that could possibly occur. Now, when you calculate probability, you're always going to be using this kind of fraction, event over total. But you are going to want to go ahead and convert that to a decimal. And the decimal is going to be rounded to 3 decimal places. So the probability that we roll a 2 is 0.167. Now, as far as interpreting, you can convert these to a percentage. So the way that you would interpret this information would be there's a 16.7% chance that we will roll a 2. Because again, that's what we're doing. We're looking at the chance of this event occurring. Now, I can switch up the event, I can switch up the experiment, and I can use this same formula to calculate the probability of different events. So the second one that we're asked to look at here says, let's find the probability that we get an even number. Now, it's important to note, once you know the total for your experiment, that's not going to change. So for any event that I want to look at here, I know I'm going to be dividing by 6 because there are 6 possible outcomes. So all I have to do if I'm switching from one event to another is make sure that I'm counting the outcomes for the event correctly. So again, if I reference my sample space and I see that I want to look at just the even numbers, again, I'm counting the possible outcomes. So even numbers are 2, 4, or 6. Counting the number of outcomes, this means there are 3 outcomes that are even numbers. Divide that by the 6 total. We have a probability of 0.5 or a 50% chance of rolling an even number. All right, so this is our basic format. This is our basic rule. Now, as we start looking at different types of experiments and different situations, you want to always keep in mind the note that I've listed here, and that is that any time you calculate a probability, its value should always fall between 0 and 1. If that doesn't happen, if you get a negative or you get something above 1, then you know something's not right. Because remember, we're talking about the chance of an event occurring. So if we look at the lowest possibility, right, 0 here is a 0% chance that the event will occur. Well, if there is a 0% chance that the event will occur, that means we're talking about an impossible event. And you can't go any lower than that. So the only time probability is 0 is if the event cannot happen. And on the flip side of this, a probability of 1 means there is a 100% chance of that event occurring. So what that's saying is that the event is certain. It will definitely happen. There is no way it cannot happen. So the last two here, I wanted to give you an example of this. If you are asked the probability of rolling a 7, all right, well, on a 6-sided die, right, you can see that's not possible. Look at the sample space. You can see that's not possible. And so when you know that what you have is impossible, you can just go ahead and say probability of this is equal to 0. All right, the other extreme here, if we want the probability of rolling a number that is less than 7, right? Everything in this experiment is less than 7. You can look at your sample space and see it. You are guaranteed to get a number less than 7. That is a certain event, so I know its probability is going to be equal to 1. Right? Those are like special cases. Everything else, when you're calculating a probability, should stay somewhere between 0 and 1. All right? So let's expand on that basic concept a little bit, and let's look at what happens if we have more than one action occurring in our experiment. All right, for example, let's say that we're going to flip 2 coins, and we want to identify the sample space for that experiment. And again, remember, sample space is just a list of all possible outcomes. Now, the main thing to note, if you have an experiment that's looking at more than one thing, each individual outcome has to look at every part of the experiment. So, we know if we're going to flip a coin, the possibilities are heads or tails. The key thing to note here, though, is because we're flipping 2 coins, every outcome has to look at both coins. So a possible outcome is not heads here, all right? A possible outcome would be heads on the first, heads on the second. And once you understand that, then you can go ahead and list out your other possibilities, right? For 2 coins, you could have heads on the first, tails on the second. You could have tails on the first and heads on the second. Or you could have tails on both. Okay, but again, notice how every single outcome looks at the entire experiment, in this case, both coins. All right, so a similar thing would happen here if I wanted to look at 3 coins. Every outcome would have to look at coin 1, coin 2, and coin 3. Now, the more items that you have to include, the harder it gets to make sure that you have all the outcomes, or even to know when you're finished. So a tool that you can use to help you when you have multiple things occurring is something called a tree diagram. And you're going to see this referenced in your homework as well. Now, what a tree diagram does is it allows you to look at an experiment with multiple parts, one piece at a time. All right, and breaking it down one at a time makes it much easier to look at outcomes. So what you do is you let every part of the experiment represent its own level in the tree diagram. So in this experiment, I'm flipping 3 coins. So I'm going to let the first level look only at coin 1. I'm going to let the second level look only at coin 2. And the third level look only at coin 3. Now, if I take the coins individually, right, one at a time, it becomes much easier to look at possible outcomes, because an individual coin can only be heads or tails. And when you go to coin 2, right, the same thing happens. If we're just looking at coin 2, it can be heads or tails. The reason this is called a tree diagram, though, is because for every level, you must branch off your new outcomes from anything that was previously listed. So second coin can be heads or tails, but I got to branch that off. And if you look at this now, you can see this is outlining our sample space for 2 coins. Right? Here's heads, heads, then heads, tails, then tails, heads, and then tails, tails. All right, so what it's doing again is just kind of laying everything out, making sure that we don't miss anything. So for 3 coins, right, I've got a third level for coin 3. It can be heads or tails, but again, I've got to branch off from any outcomes that were previously listed. And so now what I'm going to do is I'm going to make sure that I pick up every one of these outcomes along the bottom. But remember, it's got to go coin 1, coin 2, coin 3. So I'm going to have to start from the top. So my first outcome would be heads, heads, heads. And that's what we've got. My second outcome, all right, would still have heads on the first and heads on the second, but it would have tails on the third. And I'm just going to continue reading the outcomes from start to finish. So my next one would be heads on the first, tails on the second, heads on the third. Then I would have heads, tails, and tails. All right, at this point I'm right here. So starting from the top, tails, heads, and heads. Tails, heads, and tails. Tails, tails, heads. And then the last one is tails on all three. Now notice, the tree diagram is not the sample space, all right? It's a tool to help you, but you still have to write a set and list out every individual outcome looking at coin 1, coin 2, coin 3. Now, as you talk about sample spaces and outcomes and tree diagrams, I want you to remember the whole point of all of this it is to help you find probability for different types of events. So notice just for example here, now that we have identified the sample space, I could turn around and I could ask you to find the probability that all three of these coins are heads. All right, remember our method. We take event over total. Well, you can look at your sample space here and you can count. There are 8 total outcomes. And then if you look at your particular event, which is all 3 coins are heads, you should be able to note that this only happens.
Here's what I found.
That this only happens one time. Right? That's the only event where all 3 coins are heads. So using my sample space, I can say the event has 1 outcome, the total is 8, therefore this has a probability of 0.125. All right, if you can write down the sample space, you can use that to find the probability of different events. Now, something to consider about the tree diagram is that it doesn't only work for things that are repetitive, like it doesn't have to be, you know, coin 1, coin 2, coin 3. It can be 2 or 3 completely different actions that are occurring. All right, so just to show you a second example, I went ahead and laid this one out. But as soon as you notice that you have an experiment where more than one thing is being looked at, you see that and, you can write each one on its own level in a tree diagram. So I did survey response on the first level. I did location on the second level. And notice for the location, I had to branch off from my previously listed outcomes. All right, now I use that information to identify my sample space. And when I do that, I can see, I can count them up, that I have 12 total outcomes in this experiment. And that 12 should kind of make sense to you here. You know, if you think about what you were looking at on each level, you had 3 responses. And for every one of those responses, you had 4 locations. So you should be able to see that, yes, there are indeed 12 outcomes in this experiment. All right, so anytime you have something that looks at more than one piece of information, you can use the tree diagram to break things down and make sure that you're listing all the possibilities. All right, now again, the whole point of all of this is to be able to use this information to find the probability of an event. So in this experiment, again, the first thing you should note is that we're looking at more than one piece of information. So you can see that a tree diagram has already been developed for you here. Now this one is laid out horizontally rather than vertically, but it's the same concept. So what they've done here is they've looked at the first part of the experiment, which is the coin, and its possibilities are heads or tails. And then the second level in the experiment, is looking at the 8 possibilities on the spinner, right? And see how they're branched off from each one. So what you're looking at right here, this is the sample space for your experiment, right? And that's all you need if you want to calculate the probability of an event, right? So the first one here says we want to get heads on the coin, and we want an even number on the spinner. Well, the first thing I'm going to do is I'm going to look for my total, right? I can see it in my sample space, right? If I just count these up, I've got 8 possibilities here. I've got 8 possibilities here. So there are 16 total outcomes, right? And that's always going to be my bottom number. Now, the event specifically that I want is heads and an even number. So if we think about possible outcomes there, right, that could be heads in 2, heads in 4, heads in 6, heads in 8. But that's it, right? There are no other outcomes that are heads and an even number. So remember, it's about the number of outcomes. So there are 4 possibilities for the event, heads and even. We're going to divide that by our total, which is 16. So we have a probability of 0.25, or a 25% chance that we get heads on the coin and an even number on the spinner. All right, so applying the same concept, if we want to look at the probability that we get tails on the coin and a number less than 6. First thing you should note is that your total is not going to change. Once you figure out the total for the experiment, you can carry that through from one event to the next. Now, what's going to be new here is the number of outcomes included in the event. So in this event, we specifically want tails and a number less than 6. All right, so again, if I just look at the outcomes that are included, this would be tails in 1, tails in 2, tails in 3, tails in 4, tails in 5. So there are 5 possible outcomes for tails and less than 6. And again, we divide that by our total, and our probability is 0.313, or about a 31% chance that we get tails and a number less than 6. Okay, so with the use of tree diagrams, you can lay out the sample space for experiments with more than one thing occurring, and then you can use that sample space to get your total number of outcomes as well as the number of outcomes for different events. And again, anytime you're asked for probability, that's the method you're going to use, is how many outcomes for the event, and divide that by the total. Now, everything we've talked about so far has been, again, what we call classical probability, where everything has an equal chance of occurring. The other type of probability that you're going to be calculating is called a an empirical probability, right? Remember, subjective was the one that was based more on an estimate or opinion. An empirical probability simply means you are calculating it based on data. All right, so data can be given to you in a frequency distribution, in a histogram, in a stem and leaf plot, right? Lots of different ways. But the nice thing about having data is you don't have to think about how many ways could something happen. You can actually just look at your data. So one of the first things I like to do when I'm asked for probability is always look for the total first. And so when you're looking at a data set that's laid out here in terms of frequencies, to get the total for the experiment, all you need to do is add up your frequencies. Now this was done for us here. We can see that we have a total frequency of 975, and so that's what we're going to use as the total in this experiment. Now the first probability that I'm asked to find is that a person selected from this group is between 36 and 49. Now, whether it's classical or empirical, your approach to probability is always the same, and that is number of outcomes for the event divided by the total. And we've already determined for this experiment, for this frequency distribution, we have a total of 975. Now again, the nice thing about working with data is you don't have to think about how many ways could something happen. You just look straight at the data. So if I want people who are between 36 and 49, all I'm going to do is look at my data set, and it's going to tell me how many people are between 36 and 49. All right, 254. That is the number of outcomes for this event. All right, I don't have to figure it. It's sitting right there. And when I divide that by the total, that's going to give me my probability, which is 0.261. All right, about a 26% chance of selecting a person between 36 and 49. And so with empirical probability, we can use our data to look at different events. And again, all we're doing is pulling the information from the data. All right. Now, in some cases, you'll be asked to look at the opposite of an event. This is more specifically called the complement of an event. And when you see that word "not" in front of it, that kind of lets you know that you're looking at a complement, because the complement is just the opposite of an event. All right, so if I want to look at selecting someone who is not 18 to 22, right? Obviously, one thing that I could do would be just to make sure that I pull every person in this group who is not in that 18 to 22 age group. So if I take all the other groups, I'm looking at 819 of these employees that are not 18 to 22. And then we've already said total for this experiment is 975. So we take the event, we divide by the total, and we get a probability of 0.84. Now it is important to note, and this will be more important for us kind of down the road a little bit, that any time you're asked to find the probability for the complement of an event, an alternative is to simply take 1 minus looking at the event itself. All right, so just to show you that that does work here, if I were to look at those that are between 18 and 22, right, there's 156 that are actually in this age group. Dividing by the total would give me its probability. And if you go ahead and calculate that 156 over 975, the event has a probability of 0.16. And you can see when I subtract that from 1 that I am getting the same thing here for the probability that someone is not 18 to 22. Now we'll talk more about this down the road, but this is called the rule of complementary events, and it always works. If you're looking at events that are opposites of each other, you can go from one to the other by simply taking your probability and subtracting it from 1. All right, now that's as far as I'm going to go for right now.